Hey everyone, back to a new awesome video, and today we're going to continue with our series about electricity and magnetism. Today we will understand electric field. First of all, we will introduce vector fields, then we will understand by the principle of superpositions how the electric field of one particle is and how multiple particles electric field is, and finally we will draw an intuitive picture about how electric field lines go. So let's start! Great, let's first understand what a vector field really is. Imagine we have space around here, and what a vector field really is to denote a vector. It could be a force field, for example, and this vector is going to depend on the position. In that way, every single point, for example this one over here, it's going to have a vector attached to it. This vector over here is going to have another one attached to it. These are vector fields, and they will be very useful when working with electric fields and electricity in general, because we are going to assume that this field is going to be, for example, a force field, let's say, and therefore for every little point in this field, by inputting the position into this formula, this function, you are going to get the force vector. In a similar manner, you can have electric fields, in which by entering the position you are going to get the electric field vector or the magnetic field vector. And it will be very useful, as electric fields will be an object that will end up giving us lots of very important tools to understand and describe different electric and magnetic phenomena. Alright, now let's try to understand what the electric field really is. We know that the force of that a charged particle feels equals Q times Q1 times Q2 R square R hat 1, 2. However, we would like to know, for example, how a charge modifies its environment when there is no other charge around. And a very important tool will be electric field. Electric field equals the force a Q test will feel divided by that same Q test. In that way, we will have, for example, let's take the Q test to be Q2. We'll have this is Q, the one creating the field, R squared times R hat 1 T from test vector. In that way, we are going to have an expression that helps us find how a single charge modifies its environment, so that everything we have left to do is multiply this electric field by the charge that we are interested in knowing how it will behave. And by doing that, we will get how much force the electric field is going to exert on that charge. We can see from this formula that the electric field lines are going to point, in case of a positive charge, are going to point away from it to different points, and for a negative charge into it. This is negative, this is positive. Note that electric fields follow the principle of superposition. That is, if you have different charges in your field, the total electric field is going to be equal to the electric field made from 1 plus electric field made of 2 plus the electric field made from all of your charges. This need not have to be this way. For example, quarks don't behave in this way. However, unluckily for us, electric fields do, and that simplifies greatly most of our calculations. Now let's try to intuitively understand how these field lines go for different configurations of charge. If we have a positive charge, as we said before, we find from the formula of the electric field, I will rewrite over here, that the electric field, as this is positive, it's going to point from the charge to the point we are interested in knowing about. Therefore, the configuration will be something like this. And note that the farther apart we are, the arrows need to be smaller, as the magnitude is smaller too. It is not very well represented in this diagram, but if we extended one of these lines, it will go like this, and every time the arrows are smaller and smaller and smaller, because this is the case as r square. If we have a negative charge, we are going to have field lines that are going into it. Therefore, in this way, if we have a positive and a negative charge, I'm going to draw what the field lines will make here in the middle. Note that I'm not going to respect that size diminution part for the purposes of representation, but we will have some lines that we will go like this and like this in this direction, and they will curve. If we have two positive charges or two negative charges, I'm going to represent only the two positive charges, but it will be the same thing for two negative charges, just opposite direction for the arrows. We will have something like this. And note that this gives us an intuitive understanding of how electric field lines repel and attract, because when you have two charges, two equal charges, you are trying to push them together. Therefore, they are going to resist that interaction and they are going to separate, so that the field lines of these charges can go to be normal, such as those ones from that part, and they are not forced to go and open in this way, leaving this almost blank space right in there. On the other hand, when you have two opposite charges, the lines go from one to another, and they try to get together for these lines to be closer and be smaller, so that the two charges are completely together, and the lines don't be so big, like there is no lines to go in that direction because they are just in the same place. And that is how intuitively you have to understand electric field. That is all for today. I hope you understood how electric field works and you got an intuitive understanding on how electric field lines resist to getting clogged together or attract each other so that they are not so widespread. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. I hope you liked it, And remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!